This problem from the 2023 UK Senior Maths Challenge says that the expression 7n plus 12 over 2n plus 3 takes integer values for certain integer values of n, and we're asked to find the sum of all such integer values. So it's a number theory problem, and it's what we call a Diophantine equation, meaning that in this equation we're only interested in finding integer or whole number solutions. There's a few ways you could go about it, and first you might just start plugging in n values. So if we plug in n is equal to 0, we'll get 12 over 3, which is 4, and that is an integer. How about n equals 1 then? We'll get 7 plus 12 is 19 over 2 plus 3 is 5. Well, 19 over 5 is not an integer. It's slightly less than 4. Could try n equals 2, we would get 26 over 7. Again, it's not an integer. We could think about what happens as n gets larger and larger. For example, if we plug in n equals 100, we'll get 712 over 203. If we were to plug in n equals 1000, we would get 7012 over 2003. So we're getting close to 7 over 2. So as n approaches infinity, this expression approaches a limit of 7 over 2, which is 3.5. And we're approaching from above. What we started at when n equals 0 was 4, remember? And as n increases, that fraction is getting slightly smaller and smaller, but never going below 3.5. So it makes sense then that there's going to be no positive integer values of n that give us another integer, because we're always going to be somewhere between 3.5 and 4. Now, does that mean the value of 4, which we got from plugging n equals 0, is the only solution? No, because integers can be positive or negative, and we've only considered positive integers and 0. So now we want to consider negative values of n. But rather than just plugging in the negative values, what I would like to show is a method of solving this type of equation by factorizing. So what we're going to do is let this expression be k. So k here is some integer. And if we multiply through by the denominator, we'll get 7n plus 12 is k bracket 2n plus 3. Then we can expand the brackets. And what we want to do is group all our n and k terms on one side and use a technique which is similar to completing the square. Sometimes this one goes by the name of completing the rectangle. So let me show you how it works. So we've got on one side 2nk plus 3k minus 7n, and we'll leave the constant 12 on the other side. Now with those first two terms, we do have a common factor of k, so we can take that out. And now what I've got left here is a term which is 7n. And what I want is another factor of 2n plus 3, which I can then take out, and I will have 2n plus 3 as one factor and some other expression. So I can factorize that whole right-hand side. And I can do that because I can easily add a constant which I need in order to get that bracket. So I want 2n plus 3 here, but then I also have to have 7n when I expand out. So I could introduce a factor of 7 over 2 outside here, but this is a Diophantine equation, so I want to keep everything in integers as possible and without introducing fractions. So what I can do is multiply this whole equation through by 2. And then I won't have to worry about introducing a fraction. So both sides gives me 24 is equal to 4nk plus 6k minus 14n. Take out then 2k instead of 1k. The bracket would still be 2n plus 3. And then my factor here can just be 7. Okay, 7 times 2n will give me 14n. Now, if I have a 7 here, I would have a constant of negative 21 on the end. So let's just add a 21 on the end here. So the expression is still equal to that from above. And now I can factorize the right-hand side into bracket 2n plus 3, bracket 2k minus 7. And on the left-hand side, I'll just have 3. Now, this is great because 3 has only factors of 1 and 3. All right, we're allowed integers, so positive and negative, so 1 and 3 or negative 1 and 3. Which now means that this bracket 2n plus 3 could be 1. If that's the case, then 2k minus 7 must be equal to 3. Or what else could I have? Well, 2n plus 3 could be 3, and 2k minus 7 could be 1. Or each bracket could be negative 1 and negative 3 respectively. So giving us 4 choices for the possible values of n and k. Then we can easily solve each of those linear equations. The first one, for example, would give n is equal to 2 and k is equal to 5. We can solve each of the other equations in a similar way. And now we have all possible values of n and all possible values of our integer, which is k. We're asked for the sum of all such integer values, so adding 5, 4, 2, and 3 gives the total sum of 14. So this type of Diophantine equation is a perfect use case, I think, for this factorizing trick, which we can call completing the rectangle. And it's perfect because once we factorize and have a whole number on the other side, there's only a certain number of factor pairs that would give that whole number. So in this case, 3 only has factor pairs of 1 and 3, or in this case, because we allowed negative integers, -1 and -3. I mean, if we were solving over all real numbers, then this technique is probably not going to be useful, because 3 could have an infinite number of factor pairs if the factors are real numbers. But for integers, then it's a perfect use case. I hope you found that useful. If you're doing some more maths competitions in the near future, you might find a case where you can use this factorizing trick.